Talk to us today about chemical looping cycles for carbon capture, which we've heard a little bit about already, electricity generation and chemical production. So William, if you'll take the podium, the floor is yours.
Okay, I believe, there we go. So chemical looping is an interesting technology. So this presentation will differ from all previous presentations because chemical looping is still most definitely a technology that's being developed, but every sign does show that it can lead to commercial scale demonstration operations. Currently, as all these chemical looping projects that are occurring throughout the world continue to scale up successfully, this chemical looping technology does have the ability to completely transform how fossil fuels are utilized. First, though, it's kind of important to take a global perspective of how energy is consumed. So if you take a look at this chart, it's very obvious, very clear that fossil fuels dominate our initial primary energy source. And given the current portfolio for energy being oil, natural gas, and coal comprising about 80%, 60%, 80%, sorry, 80%, it's very clear that for the near future, fossil fuels, carbonaceous fuels, will continue to dominate. The world is not decarbonizing our energy, and we aren't shifting towards renewables to any great extent. Now, I realize that CCS, CCUS, CCGS, CCUGS, whatever you want to call it, is not a viable option for reducing CO2 emissions in its current state due to economic challenges and difficulties. However, that doesn't mean that in the future it can't be or won't be as research continually develops and advances. So everyone here knows the purpose of CCS. Tom and Jordan did a fantastic job yesterday going over the details of what the DOE is doing in terms of CCS. But the overall strategy does require government regulation and technological advances in order for CCS to be viable. In terms of government regulation, everyone here, the US EPA mandates and proposals have been discussed in great detail. But internationally, the European Union has also set up the emissions trading system, emissions trading system for CO2. I did steal this, in terms of technical advances, I did steal this. It's quite dated, but I did steal it from the DOE NETL, so if you guys want to prosecute me, you have every right to do so. But as you can see, chemical looping is here, and it does show that in terms of what the DOE believes, DOE and NETL believes, is that chemical looping provides the greatest cost reduction benefit, although we do take issue that and believe that chemical looping is more somewhere in this time frame in terms of commercialization. So now, what is chemical looping? It's simply a cyclical process where a chemical reaction is divided into several sub-reactions using intermediates. There are two types. One is purely for CO2 removal, and the other one is the more interesting one where it uses a metal oxide carrier particle for oxidation reduction. In terms of CO2 capture, it's typically a metal carbonate, typically limestone. It's calcined, and then CO2, a pure stream of CO2 is emitted. while the metal oxide reacts with the CO2 and the flue gas to form the metal carbonate, and the cycle continues. In terms of the redox cycles, what happens is a metal oxide reacts with the fuel, and depending on the metal oxide composition, the reactor type, you can get a variety of products, including syngas at any hydrogen to CO ratio you want. You just need to play around with the particle. You need to play around with the fuels. But syngas, hydrogen to CO ratio at any desired fraction. You can get electricity through complete combustion. You can get hydrogen. You can get liquid fuels. It just depends on how you decide to set up your reactor system. And then what you can see is that it's just a complete redox cycle between the metal oxide and the reduced metal. The main benefits, there are several of them for chemical looping, is that it is an inherent CO2 capture technology. It's not, you don't need an amine scrubber, you don't need any back-end sort of CO2 removal system. It by itself is inherently a CO2 capture technology. It provides a highly efficient method for coal and natural gas utilization, where efficiencies can range between 50% and 80%, depending on what products you want. It's fuel flexible. We have, throughout research throughout the world, has tested biomass, coal, natural gas, lignite, pet coke. Everything has been tested. And then it's also product flexible, like I said earlier, where if you want syngas at any hydrogen to CO ratio you desire, it can be achieved. You can produce electricity and value-added chemicals. The challenge is the particle development. The greatest barrier and the number one failure for chemical looping systems is the particle. DuPont had a maleic anhydride chemical looping system, but it failed because their particle continued to, or over time, failed to continue to provide the oxygen, so they just eventually ended up using an ASU. The second one is a solid circulation, where obviously on the commercial scale, it's going to be on the order of thousands of tons per hour. Not impossible, but very difficult on solids management through attrition, particulate capture devices. Everything has to be maintained. And then obviously the last one is a process integration, and that leads directly and ties in directly with the process economics. The idea of chemical looping isn't a new idea. In the 1900s, the Lane and Messerschmitt process was actually a chemical looping system for hydrogen production, very similar to what we are using today for our hydrogen production as well in a chemical looping system. The first reaction, the top one, is simply the steam iron process. The bottom reaction is the reduction of Fe3O4 back to Fe using CO. The net reaction you can see is a water gas shift reaction, but since you broke it into two intermediate reactions, there's no need for a water gas shift catalyst. There's no need for breaking the equilibrium or trying to shift the equilibrium, because there is none. It's inherently performed through the chemical looping system. And then in the 1970s, Consol Energy had the CO2 acceptor process, and what they were trying to do was they were trying to use calcium oxide both as a CO2 carrier, such that the water gas shift reaction could could move in the forward direction. Plus, since it came from the calciner, which was at a higher temperature than the gasifier, the calcium oxide also provided heat to the gasifier as well. So again, there are two types of chemical looping systems. The first one is for CO2 removal, and this has been studied heavily using carbonates, usually naturally occurring carbonates. RTI used sodium carbonate. The Europeans actually have scaled up their process to a 1.7 megawatt thermal in Hunosa, Spain, using just pure plain limestone, not doped or anything, just limestone from the ground. And what we do at Ohio State is we actually use calcium hydroxide, so we provide an intermediate reaction step to convert the calcium oxide to calcium hydroxide, and I'll go into that a little more later. Additional solids include hydrocalcites, and magnesium hydroxide as well has been studied. So at Ohio State, we have chosen calcium hydroxide because what we've noticed is that calcium hydroxide is far more reactive than calcium oxide over multiple cycles. Calcium oxide is known to degrade in cyclical fashions for CO2 capture, while calcium hydroxide has shown a steady CO2 removal. So it's a three-step process, 3 reactions, all at high temperature. The calciner is where everything starts to form the calcium oxide. That is then hydrated under using steam around 500 C, which is an exothermic reaction. So quite a bit of heat is provided through the hydrator at 500 C. And then in the carbonator, that's where the CO2 capture occurs, and then it continues in a cyclical fashion. We demonstrated this at the 120 kilowatt thermal scale at Ohio State using a coal-fired stoker donated by Babcock and Wilcox, and using direct injection of calcium hydroxide and several other oxides into our flue gas to see the removals. This is the stoker grade Ohio coal, and this is the coal flame. The single cycle studies were very successful. Calcium hydroxide showed great promise. So this was the cyclical setup where solids were injected up here and then just continued through the cycle. And this is our rotary calciner for calcination. What we were able to achieve is 90% CO2 removal at a calcium to carbon mole ratio of 1.3. This can be compared to natural limestone tested by the Europeans, where they need a 10-to-1 calcium to carbon mole ratio for 90% CO2 removal. Because of the high calcium to carbon mole ratio and the carbon to sulfur ratios, we get 100% SO2 removals using calcium hydroxide, even though we're at temperatures far lower than furnace sorbent injection, and that's just because the calcium to sulfur ratio is at least 50-to-1. In the carbonator, the residence time is on the order of seconds to achieve the 90% CO2 removal, and we've been able to sustain the reaction for several cycles. This is just a simplified process flow diagram of what is circulating through the system and the energy inputs and outputs. I like to call this slide what I did over the summer. In order to see what the effect of process parameters on the carbon capture process, the CCR process as we call it, is in terms of energy penalty, in terms of materials consumption. I started out with case 11 of the DOE baseline report. So this is the coal-fired boiler here. I apologize. I had to break this up, and it's still incredibly small. Coal and air are fed into here, and then flue gas comes out. This is the steam turbine cycle. Again, this is for the supercritical case, case 11, along with using the QG-ESS standards put forth by the DOE. And then up here is the actual carbon capture where the flue gas comes in. And then this is the CO2 compression. This is the calciner, which operates in an oxycombustion mode. And that was per the standards of the oxycombustion report, again, put forth by the DOE, as oxycombustion calciners haven't really been developed yet. And then the hydration obtain steam from the intermediate pressure and low pressure interchange. So the advantages of using this high temperature carbon capture process is that it uses limestone, which is about $25 a ton, very cheap if you get it closer to the mine. Because of the high calcium to carbon mole ratio of 1.3 to 1, our simulations show, we haven't formally demonstrated it, but all acid gases are removed, SO2, SO3, HCl, and that's just because of the trace amounts that are present and the high amounts of calcium circulating through the system. The process integration is flexible, where you can use either high temperature or low temperature flue gas. You can take steam from either the intermediate pressure, low pressure interchange, and if vacuum compression or vacuum heat exchangers are developed better, you can also take it from the exit of the low pressure steam turbine, but it is under vacuum at that point. The energy penalty, steam consumption, and oxygen consumption are all lower than amine scrubbing and oxycombustion. Under the very worst case scenario, the energy penalty is around 25%. It's usually lower, 15 to 20%, 15 to 25%. And that's again because of the amount of high pressure or high temperature heat available through hydration, the heat of reaction for hydration, and the cooling of the flue gas from the carbonator coming out at 625 C down to stack temperatures. The second type of calcium process is a pre-combustion one, where the calcium hydroxide now actually serves two purposes. One, it actually provides the steam for the water gas shift reaction upon decomposition. And second, it breaks equilibrium by capturing the CO2 and driving the reaction forward. Under the correct operating conditions, no catalyst is actually necessary to obtain high kinetics and high conversions to hydrogen. That is the only difference. The calciner hydrator remain the same. It is also a process intensification, where this is a typical calcium looping process, or calcium, not calcium, but IGCC process, where you can see all this is necessary, but because of the reactivity of the calcium hydroxide, it's reduced to this, where the calcium looping process, the three reactor system, replaces everything here. Consol Energy did an independent, with our input, did an independent Aspen simulation and economic analysis, and they also had to make a lot of additional assumptions because they were producing so much extra electricity, they didn't know how to handle that. So the total first year cost of electricity is about $92 per megawatt hour, as opposed to the coal to hydrogen based plant. And it is the lowest cost route for hydrogen production with CO2 capture is steam methane reforming plus the CLP process. Now, the more flexible and the more interesting probably type of chemical looping is the redox one, where you have a metal oxide reacting in a cyclical loop, becoming metal oxide and metal. And this is just a schematic where you can see the metal oxide enters, and then the reduced metal exits. There should be an O here. And basically, like I said, you can produce your syngas, you can produce complete combustion products, you can produce chemicals. And what you can see over here is it's still combustion, it's just that the nitrogen is over here and the CO2 is over here, so there's no dilution of the CO2. It's inherently a CO2 capture process. Again, the most critical factor for success to chemical looping is the metal oxide. The initial composition is based on thermodynamics, and then you have to go into kinetics. But what's also interesting is there is a subset of metal oxides, such as the copper oxides, that upon heating will provide gaseous oxygen, as opposed to iron oxide, which remains lattice oxygen donation. So depending on if you need gaseous oxygen or lattice oxygen, you have to make your choice there. Additional considerations are environmental health effects, cyclic reactivity, strength. So initially, the method for determining what particle to use for the metal oxide was done through trial and error, where they would just take a metal oxide, test it, see if it works. If it didn't work, they would tweak it, maybe add some additives, maybe go to a different one. Now things are becoming more scientific, where they are looking at reaction mechanisms and using density functional theory to actually determine the type of metal oxide to produce. It's becoming more of a catalytic science than it is a trial and error, which is quite positive. So far, iron, nickel, copper, manganese, and cobalt are the most common types of metal oxides. And you can also go with naturally occurring metal oxides such as ilmenite, olivine, or you can also make your own, such as iron oxide doped with something, or any metal oxide. This is version 0.0 of our syngas chemical looping unit. It's 25 kilowatts thermal, located at Ohio State University. It has since received significant upgrades. So this is just showing, again, the idea of chemical looping, where this is syngas combustion to form CO2 and H2O, but it's done in such a manner that the iron oxide does the transfer between Fe2O3 and Fe. We have tested over 300 hours of operation using all types of fuels, gaseous fuels. We've done methane, we've done natural gas, we've done syngas. What's interesting is also, because we use iron oxide, from Fe, you can go to Fe3O4 using the steam-iron reaction to produce hydrogen, and then do a dual-step oxidation from Fe3O4 to Fe2O3 using air. So this chemical looping has the ability to produce hydrogen as well. High gas conversions, high hydrogen purities, high solids conversion. And this is the process that has been chosen by ARPA-E to be scaled up at the National Carbon Capture Center in Wilsonville, Alabama. It's currently actually undergoing demonstration as we speak. We also have another chemical looping based system called coal direct chemical looping, and that takes coal, reacts it with the iron oxide. Again, you can form carbon monoxide, you can generate your syngas, you can generate your hydrogen, you can generate your electricity. And we have been able to successfully demonstrate this actually for 10 continuous days, over 300 hours of, for 10 continuous, or 200 hours, sorry, it's this one, 200 continuous hours with absolutely no issues in terms of solid circulation, in terms of conversion, in terms of operations. We were able to do it for 200 hours continuous in the fully integrated unit. We have tested coal, biomass, petcoke, lignite, PRB. Everything is fully functional. There have been no operational issues. And this has the ability, again, to use coal. So this idea of retiring coal plants, there are alternatives that do exist with encouraging preliminary economics. Of course, further testing is always necessary. Again, Consol Energy has done their own independent economic analysis, starting with their own Aspen simulations using our experimental data. And as you can see, the base plant is about 58.9. CDCL plant is about 78.4. It's less than a 35 increase in cost of electricity for preliminary economic analysis. And what's really encouraging is that the energy penalty is only 10.5%. In terms of additional chemical looping systems that are occurring throughout the world. This is the 1.7 megawatt thermal post-combustion CO2 capture using calcium oxide in Tolosa, Spain, but also Darmstadt University, ITRI, Alstom. They also have all large-scale demonstrations occurring as well. And then, in addition, you have universities such as University of Kentucky, University of Utah. You have private companies also looking at chemical looping cycles. So this is actually, all the results to date are actually very encouraging for continued fossil fuel utilization and transformations in ways that are far from traditional. Thank you.
Thank you, William. Any questions from the audience? Going once?